So now we have second, that is we have to prove second implies third. That is we have a square is equal to a and abc is equal to ac for every abc belongs to S. This we have, correct? Now we have to prove that S is isomorphic to the direct product of left zero semigroup and right zero semigroup. This we have to prove. So assume that let L is equal to S C and R is equal to C S, where C is fixed element of S. Correct? Now you can see that L is what? Left zero semigroup, and R is what? Right zero semigroup. Here. First we can see. First we can show that. You just write. First we show that L is left zero semigroup and R is right zero semigroup. Basically, just try to understand what we have to prove. This we have, and what we have to prove? We have to prove that S is isomorphic to L cross R, isn't it? Where L is what? Left zero semigroup, and R is what? Right zero semigroup. And we have to prove that our claim is what? Our claim is that S is isomorphic to L cross R. So to prove two semigroups are isomorphic. See, this is the direct product. Direct product is again a semigroup. So we have to prove that two semigroups are isomorphic. And to prove isomorphic, you know what you have to do. You have to define a map from one semigroup to another semigroup, and that map should be well defined, number one. And after that, you have to prove that map is homomorphism and 1, 1 and onto. So these things you have to verify this. But before that, this L and should be left zero and this R should be right zero. So you have to choose L, such a L which is the left zero semigroup, and R which is the right zero semigroup. So I have chosen L as S C and R as C S, where C is a fixed element of semigroup S. Right? So you write this is a semigroup. It's a semigroup. So we have to verify this. Once we are saying that it is the left zero semigroup and this is right zero semigroup, so how? Yeah, you can verify. You know what is left zero semigroup, all of you. So let's see. See, if we take two elements. Take any elements S1C comma S2C belongs to L is equal to SC. You have taken these two elements in L, correct? Now you can just see that S1C into S2C. What is the value of this? In order to prove that it is the left zero semigroup, what should come here? It should come here S1C. Then only you can say, because these two elements are arbitrary elements. What is left zero semigroup? That is AB is equal to A for every AB belongs to S. This is left zero semigroup. So in order to prove left zero semigroup, you have to prove that S1C into S2C is equal to S1C. But how it comes? See, you can also write S1 into C S2C. Now you know very well that what conditions you have, that CS2C will be written as S1 into ABC is what? AC. So it will be what? C square. And this will be what? S1C. So it is what? Reduced semigroup.
You can write from given condition. Yeah, from just you just write second.
This you have. So it implies what? It implies that L is left 0 semigroup. Similarly, you can verify by yourself, all of you by yourself, that R is the right 0 semigroup. You just write by yourself that similarly R is similarly R equal to S. Is right in the same, correct? Now define a map phi from S to L cross R by S phi is equal to SC comma CS, like it. S belongs to S. Of course, you can see that SC is going in L. L is what? What is L? L is SC. So SC is going in L and CS is going in R. So we define a map like this. So first thing is that what we have to see, that map should be well defined. You can see well that map is well defined. Y is well defined. Let S1 is equal to S2. Correct? Now it implies what? S1C is equal to S2C and CS1 is equal to CS2. That implies what? S1C comma C S1 is equal to S2C comma CS2, which implies what? Which implies what? S1 phi is equal to S2 phi. So the map is well defined, correct? Now we prove that the map is 1 1. 1 1 means, can it go reverse? Phi is well defined and 1 1. Can it go reverse? Yeah, of course. If S1 phi is equal to S2 phi, that is S1C, CS1 is equal to S2C is equal to CS2. And once S1C is equal to CS1 is equal to S2C comma CS2, that it means that S1C is equal to S2C and CS1 is equal to CS2. But does it imply S1 is equal to S2? We have to see this. See how. See, S1 can be written as S1 CS1. What? Since here you can just write from second. This you can write like this S1 CS1. A, see what? Any, you just, it means what? How can it be written as? S1 can be written as S1 square. Every element is idempotent, and it can be written as ABC is equal to what? AC, isn't it? So here S1 square can be written as S1C, S1. It follows from ABC is equal to AC. Here A and C both are S1. Here both A and C are S1. So S1 is equal to S1 square. A and C both are S1, so it can be written like this: S1 C S1. This is from the second, correct? So now you can see that S1C can be replaced by what? S2C, and CS1 can be replaced by what? CS2. Now again it will be what? S2 square, and now it is what? S2. Is it clear? So it implies what? Phi is 1. And trivially phi is onto. Why? Phi is onto. See, what is our map? Map is that like this: L cross R, and map is what? S phi is equal to this is what? SC comma CS. Here, SC comma CS. So you take any element here, for any XC comma CX belongs to L cross R, where X is what? So for any XC comma CX belongs to S cross R, there exists X belongs to S such that X phi is equal to what? XC comma CX. It implies what? Phi is onto. See, in this book, elements are written on the left side of the map, so don't worry about this, because these are the ways to write. One of the ways to write. Some books follow some different traditions, some books follow some different trends. So here, how we use this, you can write the element on the left side of the map. And some authors, Indian authors, of course, they have written S on this. It doesn't matter from where you are. But you should be uniform. So phi is onto. Now what is left? Finally, you have to prove that phi is what? Homomorphism. Phi is morphism. Finally, we show that phi is morphism. We use this term as morphism, not homomorphism, morphism. So you take any two for any elements, for any two elements S1 comma S2 belongs to S. We have to show that S1, S2, phi is equal to S1 phi, S2 phi. Correct? This we have to show. So we calculate both left hand side, right hand side. See, S1, S2 phi is what? It is S1, S2, C, comma C, S1, S2. Correct? And this is what? S1, C, comma CS2 from condition second. Correct? This we have. Now you can calculate this. As right hand side S1 phi, S2 phi. S1 phi is what? S1C comma CS1, S2C comma CS2. Now, since this is a direct product, so what should be the multiplication? It is that S1 C S2
C comma C S1 C S2.
So this is what C S2 C will be what? It is C square, and C square is what? C.
So it is what? S1 C, and similarly here
C S1 C S2. So C S1 C is what? C square, and C square is what? C S2. Is it clear? So in this way, it is what? Both are equal, and phi is what? Morphism. So in this way, we have proved that it is isomorphic to the direct product. We have proved that S is isomorphic to the direct product L cross R. Now we have to prove that third implies fourth and fourth implies first. These are easy. See, now we have third, that is S iso, that is there exists some left-view semigroup L and right-view semigroup R such that S is isomorphic to L cross R. Now we have to prove that S is isomorphic to the semigroup of form A and B, where A and B are non-fixed, their multiplications like define A1 B1 into A2 B2 is equal to A1 B2. So in this, what you have to do is very simple. You just take A as L and B as R. Already you have proved that S is isomorphic to L cross R, correct? This you have. This you have. Now take L as A and take R as B. Now what you have to do, you have to just you have to verify the multiplication, that the multiplication given should be like this or not. You have to verify this. Now it's very easy. See that A1 comma B1 into A2 comma B2, it will be what, students? That is A1 A2 comma B1 B2, because it is a direct product. Now see, A1 A2 both are the members from where? It is from A. B1 B2 are the members from B, and A is left view semigroup, so A1 A2 will be what? A1. And B1 B2 are the members of B, and B2 is what? Right view semigroup. So what is B1 B2? That is B2. Proof. So A1 B1 into A2 B2 is what? A1 B2. This you have to prove. Answer is proved. So third implies fourth. In a similar way, now remaining is what? Last one, that is you have to prove fourth implies one. That is this. S is isomorphic to a semigroup of the form A cross B, where A and B are non-empty sets and where multiplication is defined like this. And now you have to prove that S is what? Rectangular band. So if two semigroups are isomorphic to each other, and if we are able to prove that one semigroup is rectangular band, then another semigroup being isomorphic to the next one also becomes rectangular band. So what we have to do, we have to prove that A cross B is a rectangular band. If we prove that A cross B is a rectangular band, then S being isomorphic to A cross B become automatically rectangular band. So in order to prove this is a rectangular band, what we have to do, we have to take three elements. We have to show the condition of rectangular band. That is ABA is equal to A for every AB belongs to S. But here AB are the members of the direct product AB. So element should be in pairs. That is fourth implies first. For any A1 comma B1 A2 comma B2 belongs to A cross B, A1 B1 into A2 B2 is equal to A1 into A1 comma B1. You have to calculate this. That is, for example, this is A, this is B, this is A. If ABA comes A, it means that it is rectangular band. Correct? So you can calculate, just follow associativity. That is, it will be what? How multiplication is defined? This is A1 comma B2. Now this is A1 comma B1. Now A1 comma B2 into A1 comma B1, it again comes A1 comma B2. It implies that A cross B is a rectangular band. it implies that S
Is a rectangular band. As is isomorphic to A cross B.
S is a rectangular band as S is isomorphic to A cross B. So in this way we have proved first implies second, second implies third, third implies fourth, fourth implies one, and this whole theorem in this way it is proved. So I stop here. So I will continue lectures in the future days, and I hope all of my students watch seriously all my lectures, because when I am doing labor for all of you, so I also expect from all of you that all of my students watch every second of my lecture, and wherever they feel any doubt, they can post it in the comments, and they can ask me, they can call me, and through Zoom I can interact all of you. So there are many ways to interact, there are many ways for the discussion, but for all of this, all of the students must have interest in that. So I am motivating all of my students so that they develop interest in themselves, because when you study and when you develop interest in yourself, and when you study, you will get something, you get understanding of the subject, and you will get good score in the marks. You can score good in the marks in the mark sheet, and your future will be bright. So I hope that all of you cooperate, and wish you best of luck. Thanks a lot.